We reintroduce sequences for this portion of the optional topic, and we're going to be looking at the convergence or divergence of sequences and series. And the notation a sub n with brackets around it denotes an entire sequence, so it means plug in 1, 2, 3, 4, 5 into whatever rule happens to be in here. And if L is a real number, then we can say that the limit of a sequence is L as n goes to infinity. If that limit exists, then our sequence will be converging to that number. If the limit does not exist, the sequence diverges. So here we have three sequences that we want to determine convergence for. So let me cover these two up first. So we want to find what's going on with this in terms of its limit. And a lot of times it can be useful to think of what these terms would be. A sub 1 is equal to 2. A sub 2 would be 4. A sub 3 is 2. A sub 4 is 4. And so on. This repeats itself. So for this particular sequence, there is no limit. So this sequence diverges. Looking at the second one, here we want to look at the limit of b sub n as n goes to infinity. In other words, what is the limit as n goes to infinity of n over 1 minus 2n? That's the rule for our sequence. And we've dealt with things like this before. Dividing everything by the highest power of n. This is equal to negative 1/2. So this sequence, b sub n, converges to the value negative 1/2. If you were to list out many terms for this, we would find that it's getting closer and closer and closer to negative 1/2. And now for the last one, we want to look at this limit. And this isn't a polynomial problem like the second one where we could divide everything by the highest power. This is something that's in indeterminate form. The limit here is equal to infinity over infinity. And we can use L'Hopital's rule to deal with this. So I'm going to take the derivative of the top and the bottom. So on top I'll have 2n. On the bottom I will have the natural log of 2 times 2 to the n. And this is still in indeterminate form. It's still infinity over infinity. So we can apply L'Hopital's rule again. And this ends up being 1 over infinity, which does converge to 0. So this sequence, n squared over 2 to the n minus 1, will converge to 0. There's another test that we can use called the squeeze theorem to tell if something converges or not. And what it says is that if two sequences, a sub n and b sub n, as n gets really big, are the same. They're equal to L. And there exists some n in the integers such that a third term will always be in between the terms of a sub n and b sub n for all values of little n greater than this number. This backwards e, just to make a note here, this means there exists an n in the integers. And this upside down capital A means for all n greater than capital N. So kind of what's happening here is we have these points for a sub n approaching some limit, and then we have some points for b sub n also approaching that same value of L. And if at some point our sequence C is always sandwiched in between them, we can say that that also has to be approaching L. It's being squeezed in between these other two functions. So we have sequence C sub n defined as -1 to the n times 1 over n factorial. We want to show that this converges, and also we want to find its limit. This is something that, well, we can't just flat out find the limit for. We don't have any skills for that so much. We can't use L'Hopital's rule. We have this factorial. -1 to the n, that's not nice. And what we want to do is we want to compare this to two other functions that approach the same value. -1 over 2 to the n, that has a limit of 0, and 1 over 2 to the n has a limit of 0. The limit of both of those is 0. And if we look at the terms for this, we can draw a comparison and make a squeeze with our function c sub n, with our sequence c sub n. So if I list out a sub n, I get 1/2 -1/2, -1/4, -1/8, -1/16, and then b sub n is 1/2, 1/4, 1/8, 1 over 16. And then the terms that we're actually dealing with, those would be -1 to the first over 1 over 1 factorial. So the first term is -1. The second term would be positive 1/2. The third term would be negative 1/6. The fourth term, 1 over 24. The fifth term, -1 over 120, and so on. If we look at these terms and look at 2 to the n versus n factorial, because those are really the defining features of a sub n, b sub n compared to c, we can say that n factorial is going to be bigger than 2 to the n for n greater than 4. If we look at the terms here, what that would mean is that if n factorial is bigger, then our c value is going to be less than b sub n, and it's going to be greater than a sub n. So what we've now determined, and this should be equal to, so starting here, those terms are always in between these two convergent sequences, and what that means is that the limit of our sequence by the squeeze theorem is equal to 0. And in general, we can say that k to the n over n factorial as n approaches infinity is 0 by the squeeze theorem. We'll always be squeezed in between these two a sequence and b sequence as n gets really big. Depending on what k is, it will determine what term it starts being between there. But what the squeeze theorem says is that for all n greater than some number, in this case it's 4, but for some number, capital N, all of the n's bigger than that will always be between a and b. So this is something worth remembering. Couple more examples. We have these 5 terms. It's an infinite sequence. We want to know, does this converge or diverge? Well, to deal with that, it would be helpful if we had a rule for it. And a rule that we could write is that the numerators are all powers of 2. 2 to the first, 2 squared, 2 cubed. So the numerators are 2 to the n. The bottom are odd numbers. And the way we write an odd number is 2 times n minus 1. And we can check that with 1, 2, 3, 4, and 5 for n, and we generate these terms. Now we look at the limit as n goes to infinity of a sub n. And what we have here is indeterminate form. It's equal to infinity over infinity. So what we need to do is we need to use L'Hopital's rule. And this is equal to infinity, so this is divergent. We could say that a sub n is divergent. It doesn't approach some value. It blows up as n gets really big. Here's another sequence. This is an alternating sequence, and we want to know, does this converge or diverge? And we're going to use this theorem in the orange box that says if the limit of the absolute value of a sequence is 0, then the limit of our sequence is 0. So let's look at a rule for a sub n. Since they're alternating terms, we need -1 to a power, and we can either use n or n plus 1, determining based on what we need for the first term. The first term here is negative, so we want -1 to the first. We want -1 to an odd power. And then we write a rule that actually deals with our individual values. And some of these things are going to be easier than others. The denominator are values of n factorial. 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. And then the numerators are actually all 1 less than the powers of 3. So now let's look at the absolute value of a sub n. And then its limit. And based on what we had right here, k to the n over n factorial, that's essentially what we have here. 3 to the n minus 1 is pretty insignificant, over n factorial, this is equal to 0. So, negative 2 over 1, 8 halves, negative 26 over 6 converges. By this theorem that we have right here. Another useful thing that you should get to know. So here's the first assignment. We'll do the rest of 9-1 in the second portion of this.